Good morning, everyone. We are Group 5. I am Xander Craner.
I'm Jeffrey Perez.
And I'm Stanley Zhang.
And today we'll be discussing the Lennard-Jones interatomic potential energy for aluminum and iron and how this model can help us understand the mechanical behavior of these two important metals. In this presentation, we'll discuss how we model the interatomic distances for aluminum and iron, how we use those models to estimate their elastic and bulk moduli, and how vacancy formation energy affects their strength and defect behavior. The foundation of our analysis is the Lennard-Jones potential, which models the energy between two atoms as a function of their distance. Here, R is the interatomic distance in nanometers, and U of R gives us the potential energy in electron volts. The first term represents a strong repulsive force when atoms are too close. This is the interaction of overlapping electron clouds. The second term represents attractive van der Waals forces that dominate at moderate separations. The point where the potential energy is at a minimum corresponds to the equilibrium distance between the two atoms. That is the natural spacing of the crystal lattice. To find the equilibrium distance, we take the derivative u of r with respect to r and set it equal to 0. Solving for r, we find the point where attraction and repulsion balance out. For aluminum, this distance turns out to be around 0.286 nanometers, and for iron, around 0.248 nanometers. These values are consistent with experimentally measured lattice constants. Aluminum has a face-centered cubic structure, while iron, at room temperature has a body-centered cubic structure. These interatomic distances form the foundation for predicting other material properties.
Elastic and bulk moduli. The elastic modulus or Young modulus describes how resistant a material is to elastic deformation under stress. In simple terms, it's a measure of stiffness. Using interatomic potential models like Lennard-Jones, we can estimate elastic modulus by examining how the energy changes as atoms are slightly displaced from their equilibrium positions. Mathematically, it's related to the second derivative of the potential energy at equilibrium. Our equation is shown over here. When we calculate or compare experimentally, aluminum Young's modulus is roughly 70 GPa, and iron's Young's modulus is about 210 GPa. That means iron is about 3 times stiffer than aluminum. But why? This difference arises from the stronger metallic bonding in iron. Iron's d electrons contribute to a higher bonding strength and therefore steeper potential energy around the equilibrium. Bulk modulus comparison. The bulk modulus measures how resistant a material is to the volume change under uniform pressure. In other words, of quantifying atomic bonding strength. Using similar principles, the bulk modulus can also be derived from interatomic potential curvature. The approximate values for aluminum is around 76 GPa, and for iron, it's around 170 GPa. So again, iron's atomic structure leads to higher resistance to compression. In general, materials with steeper potential energy curves have higher moduli and stronger bonds. Vacancy formation and defects. Next, let's move from perfect crystals to defective crystals, specifically vacancies, which are missing atoms in the lattice. Conceptually, the vacancy formation energy, EVE subscript VEV, is the energy required to remove an atom from the lattice and create a vacancy. It tells us how likely defects are to form at a given temperature. Aluminum EV is 0.66 and iron is 2. So it takes about 3 times more energy to create a vacancy in iron than in aluminum.
So the equilibrium vacancy concentration can be estimated by the equation, which is shown here. So you have N sub V equals to N times the exponential of negative EV over KT. And in this scenario, N is going to be the number of atomic sites. K here at the bottom is going to be the Boltzmann constant. And T is going to be the absolute temperature, which is just, it's usually in the form of Kelvin. And in this, we have some examples. So for instance, we picked a temperature that's about 700 Kelvin. And at around 700 Kelvin, when we use this equation, we realized that for aluminum, where, by the way, aluminum would be plugged into your EV and your N, and you would plug that in, and when you get the answer, it's about 10 to the power of 22 per cubic meter. More specifically, it was around 7.75, but just for the sake of engineering, we rounded up to about 10 to the 22nd power. And this is the same case for iron, where iron was about 10 to the 18th. So just looking at this broadly, you can definitely tell that iron has much lower vacancy concentration than aluminum. And what that means is that although iron is going to be more stiff, or aluminum is going to be more weak per se, aluminum is going to have higher magnitudes of vacancy at the same temperature as iron. And so one of them would be easier to break, one of them would be harder to break, which is just iron and aluminum. And now vacancy probability and yield strength. So just a brief overview. Vacancy probability is, in short, just what are the chances that any atomic site is vacant. So if you take like a box, for example, and you shift it in a shear stress, you're gonna see like there's a chance that some parts are gonna be empty, some parts are gonna be full in a very, very atomic scale, similar to what we have in class. And this is basically just a method of finding out what are the vacancy probabilities using a certain formula. And in this formula, we have P equals to NV divided by N. And as you can see over here, we have NV divided by N. And basically what this is saying is you take the vacancy and you divide it by your N value, which is dependent on your atom. And that's how you find the probability. So if it has a higher vacancy, it's going to have a higher probability. And if it has a lower N value, it's going to have a higher probability as well because they go hand in hand. Now, if you look back at aluminum, aluminum's vacancy was about 10 to the 22nd power, and iron was at 10 to the 18th power. And so what that means is since aluminum is a much higher amount of vacancy, it's also going to have a higher probability for the vacancy. And so it's the same vice versa for iron. Because iron has less vacancy, there's going to be less probability of vacancy. And so what does this actually do? So vacancy probability affects the yield strength, because as you have more and more gaps in between as you're bending something, then you also have a higher and higher yield strength, or a lower and lower yield strength, because you don't want something to bend and have a lot of little holes. You want something to bend and keep its atomic structure as it's going down. And so over here, higher vacancy concentrations allows for dislocations to move more easily, which is where the analogy of breaking something comes in. And so when you have more dislocations, it lowers your yield strength because there's more gaps for the things to shift around. And so for aluminum, if you ever played around with aluminum foil, you'll realize that having a thin sheet of aluminum foil and you can bend it back and forth all day and it won't break. But if you try to do that same piece with like a sheet of iron, with a sheet of titanium, with anything like that, where it's a very, very brittle metal, if you try to do that, it would just fracture immediately. So that's one of the reasons why aluminum, which is, although light and ductile, is relatively soft as compared to iron. And so this is just a table that we have. This is one that we created for everything that we just went over. And just to review, so we have the property that we're looking at. We have our have our chemical, we have our second chemical or atom, and then we have our comparison. So in this scenario for interatomic distance for one, well, just a brief overview. Aluminum is going to be more ductile than iron. And what that means is basically it's a lot easier to bend, a lot easier to shift around, and iron is going to be a lot more brittle. And in this scenario, interatomic distance, because aluminum has a larger spacing, that's what's going to let it have more flexibility. If you have like two pieces like this, you can shake it around a lot, but if you have this, they're all going to be stiff. So that's one of the reasons why aluminum is going to be more flexible. Young's modulus, since aluminum has a lower Young's modulus, that's how you can tell iron is going to be a lot more stiff than aluminum. And Young's modulus, just a quick review, is just how stiff something is, or like the elastic potential of it. The bulk modulus, again, iron is going to be higher, so it's going to be more stiff. The vacancy energy, you have 0.66 eV to 2 eV, and so that means that iron is going to be more stable. And when you have more stability, you also have less change as you bend it, which is going to lead to more stability and tensile strength. And down to vacancy concentration, because aluminum has a much higher rate of defects, it's also going to have a lot more vacancy and vacancy concentration, which leads to it being able to bend a lot easier than having something like iron. And going back to the yield strength formula, which was NV over N, because it has a very, very high vacancy concentration, it's going to have vacancy concentration and vacancy strength go hand in hand. So your NV is going to be a very high value. But if your NV is a high value, your N has to be a high value as well, just to cancel things out. And when you divide, it's going to be a lower chance. So when you do the calculation for aluminum, you only get a 70 MPa, while iron would have 250 MPa. And so basically that just says iron is going to be stronger in the stiff form. And one more thing, what exactly is Lennard-Jones interatomic PE? So Lennard-Jones interatomic PE is going to be basically a framework that you can use to understand atomic interactions. And so when you have this, you can understand just what happens on a molecular scale and an atomic scale of the structures. And we went over this in class, but if you take a shear stress on a box and push two parts aside, you can see how many pieces are have empty spaces as you're breaking it through. Like if you break an ice cube, you can see that there's a lot of fractures. All of those fractures are due to the Lennard-Jones potential. And in short, that's basically how you can tell how strong something is, how something will break, and it can be used in various forms of equations other than this one, which we're not going to go through for today.
So iron's smaller interatomic spacing and steeper energy curve, they lead to a higher stiffness and strength. In contrast, aluminum, with its lower bonding energy and higher vacancy formation rates, is softer but more ductile. These differences in atomic scale behavior explain why iron is used in load-bearing applications, while aluminum is chosen when low weight and ductility is key.
So again, iron, because it's very good at load-bearing applications, iron is actually one of the key components in making steel, which is very strong for load bearing and is used in various forms such as solar panels, houses, skyscrapers, used in all sorts of things. And iron is one of the most inexpensive and one of the best at load bearing. So if you put in a few things such as bronze or any other material that allows it to not rust, steel becomes a lot stronger at load bearing because of the iron, but it doesn't have the rusting properties that iron would have.
And along with that, because iron is so dense, it's not suitable for all applications. For things like airplanes, aluminum is used because as it is strong as well, it is also a lot less dense in applications that weight really makes a difference, specifically airplanes.
And that's it. Thank you very much.